Welcome to Easy Math TV. We have another video on probability here for our statistics courses, and we're going to just continue from our previous video. So if you didn't see the one right before this, stop the video and go back and watch part 1, and this is part 2, starting with question number 8. So just some examples in probability that involve statements like and or, and then conditional probabilities as well. So the first question here involves calculating probability from something called a contingency table. So let's talk a little bit about what information is given here. So in this table we have basically these are just orders. These are fast food restaurant customers who order via a phone app. So basically restaurant A, restaurant B, restaurant C, and restaurant D are probably chains of some kind. And they each allow customers to order via a phone app. And data was collected on probably a sample of customers where they wanted to see how accurate or inaccurate the orders were once the customer picked up the order. So what did the customer actually receive what they ordered? And the numbers are spread out, as you can see here. So when you look at a table like this, the numbers are given to you as distinct numbers. So basically, this 340 that you see here is only pertaining to the orders from restaurant A that also were accurate. Okay, so these are the and probabilities. So if you wanted to know what the probability of an order being from restaurant B and is accurate, you would need the 266. Okay, so everything that you see here is considered to be disjoint or separate. Okay, so we've separated out all the orders based on what restaurant they came from and whether or not they were accurate. Okay, so the accuracy is across the row and the restaurant is in the column. And what we need to do then is calculate all of the totals. So how many orders were there from restaurant A? You just add the 340 to the 37, and we get 377 there. The total number of orders from restaurant B is 317. The total number of orders from restaurant C is 266. Again, just add those numbers. And the total number of orders from restaurant D was 139. Okay, so we didn't have the same sample sizes from each of the restaurants. And then you can go across and you can figure out exactly how many orders in all we were looking at. So add up the numbers at the bottom here, and you get 1,099. So adding these four numbers up, you get 1,099. And it just so happened that they were split up among these four restaurants. Okay, so then these totals also have to be calculated. So basically, what was the total of all of the accurate orders? So if we wanted to know how many orders were accurate out of the 1,099, we would have to add up all the numbers in that row. And that number is here, so we can reveal that. That's 968. So 340 plus 266 plus 234 plus 128 was 968. And whatever's left over has to be here. So this number should be equal to, so you can check your math by making sure that if you add up these four numbers, you should get this number here, which is 131. So you can double check that math yourself. Just pause the video if you want and just go ahead and add up 37 plus 51 plus 32 plus 11. See if you get 131. And then double check to make sure that 968 plus 131 is in fact 1099, which is all of the orders that we were looking at. Okay, so that completes the table. All right, we're going to be using all of those numbers to calculate some probabilities here. There's four situations. So let's take one at a time. If one order is selected, find the probability of that order being either not accurate or is from restaurant C. So the restaurant C orders were 266 out of 1099. And then it says not accurate. So the not accurate ones are over here, 131. So because of the or statement, we are going to be using the addition rule. Okay, we're going to be using the addition rule. However, we need to know that the 266, if we count those, and we also count the 131, then we have accidentally counted the 32 that are in this block twice. So we're going to have to subtract that off. So because we've accidentally counted it twice. So orders from restaurant C plus orders that were not accurate minus the orders that were both. And then divide that by 1099. So this is what that looks like as an equation. 131. So I put parentheses around this because we want to add those numbers up first and then divide by 1099. So that's the total number of orders that we're actually looking at, like the total number of orders that were either from restaurant C or were not accurate is 131 plus 266 minus 32, because we accidentally counted the 32 twice. And when you divide that by 1099, we get a decimal 0.33212. So it's roughly 1/3, approximately 1/3. 0.333 repeating is 1/3, so that's pretty close to 1/3 that are either from restaurant C or were not accurate, okay? And then the question that follows that is, are these events of selecting an order that is not accurate and selecting an order from restaurant C, are they disjoint? So are they disjoint events? And because we had to subtract the number that was in both, we can very confidently say that the orders were not disjoint because there were a certain number that were in both that we had to account for. So no, because there were 32 outcomes that were both not accurate and from restaurant C. So when you have numbers that satisfy both conditions, they are not disjoint. Okay. Let's look at the second probability question based on this table. Suppose we select two orders. So we just randomly pick one order and then we select another order. Find the probability that they are both from restaurant D. And there's two ways that we're selecting them. So what if the selections are made with replacement? So let's talk about with replacement first. If we're making the selections with replacement, it's just you take the probability that it's from restaurant D and multiply by the probability that it's from restaurant D again, because we're looking at that happening twice. So if we want the restaurant D event to occur twice, we take the probability of it and multiply it by itself. So this is what that looks like. 139 out of 1,099 orders. That's from restaurant D. Multiply that by another order being from restaurant D. And again, see that the numbers didn't change because it's with replacement. So I put that order back in the file folders, and we're just randomly selecting one again, and it's still 139 out of 1,099 chance of selecting it. So when we multiply those together, we get 0.015997. So it's approximately 1.6% chance, a 1.6% chance, which is pretty unlikely, pretty rare. Now, what if the selections were made without replacement? So this is what we call conditional probability. Conditional probability means that the second selection is impacted by the first one. So the first time you choose a restaurant, being from restaurant D, is 139 out of 1,099. But the second time that you select one, we are down one selection. So we've already removed one from the pot, if you will, or the file folders. So there's one missing. And so if you've already removed a restaurant D, then we're down to 138, and the total is also down by 1 to 1,098 instead of 1,099. So here's what that calculation would look like. So the first selection would be 139, one of the 139 out of 1,099. And then the second selection is one of the remaining 138 out of the remaining 1,098. So that's called conditional probability. And I didn't use some fancy formula. I was just considering what the new probability would be of making the second selection if one of those 139 had already been removed. So the probability isn't going to be drastically different from the one we just did, just because there were a lot of selections here. Out of 1,098, you haven't really reduced it by that much, but it is slightly different. So the new calculation here is 0.015896 instead of the 997. So it's still going to be somewhere around 1.5%. Had these numbers been a bit smaller, then you would see a drastic difference between those two, but it's not that much. So that's the difference between probability with replacement versus probability without replacement. The second probability is going to be impacted by the first probability. So now the next question, an order is randomly selected. What is the probability that the order was for restaurant A, given that it was accurate? So that is a very important phrase right there. So I'm going to highlight that in blue, given that. So we are assuming that the order was accurate. If we're assuming that the order was accurate, then we're going to be dividing by the number of accurate orders. Instead of dividing by the total number of orders, we're only going to be dividing by the accurate orders. And the reason for that is because we're assuming that has happened. That has already occurred. That's a certainty. So we've reduced the number of possibilities from 1,099 to 968. Out of those accurate orders, what is the probability that it was for restaurant A? So all we have to do is look across on our table how many in that row. So we're just looking at that row now. How many in that row were from restaurant A? And that's 340. So we're going to just take the 340 and divide by the 968. So that whenever you're assuming something is true, that's limiting you to either a certain row or a certain column. And it's based on the thing that you're assuming to be true. So in this case, we're assuming that the order was accurate. So that is the number that goes in the denominator of our fraction. That's the thing we're dividing by. There's our 968. So 340 divided by 968 is 0.35123967. So that's how many decimal places I had on my calculator. But suppose that the directions said to round to the nearest thousandth or 3 decimal places. So I have to count over 3 decimal places. That's the 1 here. And look at the next digit. So if the next digit is a 5 or more, I'm going to round that up. If it's not a 5 or more, we will just keep it a 1. So this is 0.351. And then the last question that we're asking from this table is, an order is randomly selected. What is the probability that the order was not accurate if it is known that the order was from restaurant B? So now we're assuming that the order was for restaurant B. So where are the restaurant B? Here's restaurant B here. That's the total for restaurant B. So if we're assuming that that is true, right? That is being assumed to be true. So now we're only interested in calculating probabilities in that column. Out of the 317, because we know we're in restaurant B, so we can ignore everything else. So it just says, what is the probability that the order was not accurate if it is known that it was from restaurant B? So now we just want to know how many were not accurate in that column, which is 51. So we're going to be dividing 51 by that 317. 51 divided by 317 is 0.16088,328. And again, if we're rounding to 3 decimal places, we count down, so 1, 2, 3. So either the 0 is going to remain a 0, or based on the digit that comes next, we will round it up. So because of the 8, the 0 becomes a 1. So this is 0.161. All right. And one more question here. Testing for a disease can be made more efficient by combining samples. If the samples from 6 people are combined and the mixture tests negative, then all 6 samples are negative. On the other hand, if you happen to mix a positive sample in with a bunch of negative samples, the sample itself, the mixture, will test positive. So this was done during COVID-19. People had their samples tested by combining samples into groups and having that group tested. And if an entire group tested positive, then everybody in that group had to be tested again. It saved a little bit of money. So assuming that the probability of single sample testing positive is 0.05, find the probability of a positive result for 6 samples that are combined into one mixture. And then, is the probability low enough so that further testing of the individual samples is rarely necessary? So we're trying to answer the rare question here. So the first thing that we need to note is that we're looking at the probability of a mixture testing positive. And so by definition, that's equal to the probability of at least one of the samples in that mixture testing positive. So this is an important formula for us. The probability of at least one is equal to 1 minus the probability of none. So sometimes the probability of none is easier to calculate than the probability of at least one. So we use this fact. Okay? So in other words, the probability of at least one positive result is equal to 1 minus the probability that they are all negative. So in answering that question, let's just take it step by step. The first step then is, what is the probability of a single sample testing negative? Because we know that testing positive is 0.05. So that means that the probability of testing negative is 1 minus 0.05, which is 0.95. So the next step then would be, what is the probability that all 6 samples test negative? And that's just going to be 0.95 times itself 6 times. So that's the straight up multiplication rule. These are independent samples. So when you have independent samples, you're just going to be multiplying the 0.95 times itself 6 times. And that turns out to be 0.73509. Okay, so we just used the multiplication rule there. So then the last step then is to take that number and subtract from 1, because the probability of at least 1 is 1 minus the probability of none. So that's going to equal 0.265 if we round it to 3 decimal places. So our conclusion then, because 0.265 is much greater than 0.05, so that's like 26.5% of the time. So it is not low enough. It's low, but it's not low enough so that further testing is it is in fact more than rarely necessary. So that it does not satisfy the rare event rule. It's slightly greater, it's slightly more than rarely necessary. I mean, you could say that it's less common, but it's not rare. It's not going to be a rare event. So we are going to need further testing, and it won't in fact be a rare event. The further testing could occur around 26.5% of the time. Okay, so that would be our conclusion for that. And then, so just to point out one more fact, there's a term that we use in statistics and probability called the confusion of the inverse. The confusion of the inverse in conditional probability is the false belief that the probability of A given that B has already occurred is the same thing as the probability of B given that A has already occurred. In other words, the order, these two probabilities are in fact the same. But this statement here is generally false. This is a false statement. So this is not true. So I'm just going to put a note here, not in fact generally true. So that's it for our videos for today. Like, subscribe, comment down below. I hope this helped you. And this was basically all that we were going to cover today in our class today that we would have had had it not snowed. So thank you for putting up with this, and I'll see you. We will talk about some more probability next time, and that's it for today, and I'll see you in the next video.